Hello, everyone. Welcome to pre-lecture 17. Hope you all have had a good spring break and are ready to get going on the chemistry again. So we'll dive right in. We're going to be continuing with our acids and bases. And in particular, we're going to be talking about salts today. And so consider that you dissolve some sort of salt, such as ammonium chloride in water. Anytime you dissolve a salt, it can be acidic, basic, or neutral, and that will depend on the acid-base strengths of the constituent ions. And so again, in this example, we're looking at ammonium chloride, so that's NH4Cl. It starts as solid. Once we dissolve, we get, of course, ammonium and chloride. And so the ammonium we should recognize as one of our conjugate acids for the weak base ammonia. And so this product will undergo a second reaction where this ammonium will react with water in order to form hydronium, our H3O+, as well as ammonia, NH3, right? And so because of this, overall, that solution, despite dissolving just a salt, will end up being acidic, right? We can also think about the anion. So in this case, our anion is chloride. And so if chloride undergoes some sort of acid-base reaction, it would react with water in order to form hydroxide as well as hydrochloric acid, HCl. But what we know from our previous work is that this reaction entirely favors the reactants. We know that if we have HCl in solution, it will fully dissociate, especially if there's an equivalent of hydroxide that it can react with. And so our chloride, our Cl minus, is not going to have any effect on the pH of our solution. So for example, instead if we were dissolving sodium chloride, then our solution would remain neutral. But in this case, because we dissolve ammonium chloride, overall the solution would end up being acidic. Okay? Right. The same can, of course, be true for things that are basic. And so in this case, similar example, but looking at the salt sodium acetate, so NaCH3CO2, the solid, and if it is dissolved in water, it will dissociate to form sodium, Na+, and acetate CH3CO2-. So in this case, our CH3CH2- will be what reacts with water in order to perform an acid-base reaction where we form hydroxide as one of our products, and then the weak acid, acetic acid, as our other product, that HCH3CO2. Okay. And so from there, we can also, of course, consider our cation, in this case, sodium. And this may also undergo an acid-base reaction. If it were to react with water, it would, of course, form sodium hydroxide and then H+. But again, based on what we talked about prior to spring break, we know that sodium hydroxide is a strong base, and thus it will fully dissociate in water, meaning that reaction entirely favors the reactants. And that means that the sodium will have no effect on the pH of the solution. And so overall, with this solution, when we dissolve sodium acetate, we will end up with a basic solution because we form hydroxide as part of our products. Okay. And so I want to do a practice problem real quick here. So let me just get my drawing tool up and then we can go through this. So in this practice problem, it says determine the acetic acid concentration in the solution where we start with acetate, again, our CH3CO2-, and we're given a concentration of that at 0.050 molar. We're also told that our concentration of hydroxide is 2.5 times 10 to the negative 6th molar at equilibrium. Now, what this question wants us to do is find the Ka for acetic, or we're also given the Ka for the acetic acid. We're trying to determine the concentration. So if we were to start doing that, a great place to start, I know I've said this before, I will continue to say it, is just write the chemical reaction that you believe is going on, as well as the equilibrium expression that would accompany it. And so in this case, we're starting with CH3 CO2 minus our acetate, which is, of course, dissolved in water. It will be reacting with that water, which is a pure liquid, and it will be in equilibrium with our products, OH minus, our hydroxide, as well as our acetic acid, which is what we will, of course, be solving for. So the CH3CO2H. That is, of course, dissolved as well. Okay. If we were to write an equilibrium expression for this, Ka, or I guess we could just start by saying K. How about that? Because it is not, in fact, Ka, it is Kb. And the reason it is Kb is because our ion of interest, our acetate, is reacting with water and it is acting as a base, meaning that instead of using Ka, we'll be using Kb. And so Kb is equal to, as with all of our equilibrium stuff, our products over our reactants. So we can put our concentration of hydroxide over concentration of acetic acid, O2H, then divide that by the concentration of our acetate ion, CH3CO2 minus. Right? And so in order to solve for this, the variable, of course, that we want to solve for is this acetic acid concentration. We're given our concentration of hydroxide, right? We're also given our concentration of acetate. So all we should need to solve for this is Kb. And so we can use an equation that we talked about before break, where we can, or I will remind you, we can use our Kw relationship. So Kw equal to Ka times Kb. And so in this case, in order to determine Kb, Kb is equal to Kw divided by Ka, right? And so if we plug in those values, Kb is equal to 1.0 times 10 to the minus 14. Kw is a value that you should know and have memorized. So 1.0 times 10 to the minus 14th divided by our Ka, which is what is given in our problem. So our 1.8 times 10 to the minus 5. And when I plug that into a calculator, I got a value of 5.6 times 10 to the minus 10th for Kb. And so if we set that equal to our other known values, again, our concentration of hydroxide we're given in our problem. So concentration of hydroxide, 2.5 times 10 to the minus 6 molar. We are solving for our unknown concentration of acetic acid, CH3CO2H. And then that will be divided by our concentration of acetate, which we're given in the problem, which is this 0.050. And so we have three knowns, one unknown. You can, of course, do the algebra in order to solve for that. And so when you do, you should get CH3CO2H is equal to a value of 1.1 times 10 to the minus 5th molar. That would be our concentration of acetic acid in the solution with the conditions described. Okay. Right, I hope that made sense. I'm just going to clear these drawings real quick. And then that will be the end of our pre-lecture video. If you had any questions, of course, feel free to reach out via email or via, or just be ready with questions in class. I will see you on Tuesday and hope you are well. Bye.